whenever.
Okay, what I want to demonstrate here is a solid state electric generator. The principle is based on balanced flux paths. This device laid out here is soft iron path, you see here, made up of what appears to be an H with the two bars down here and figure 8 closed up, and these are magnets down the middle. Now, this is strictly just to prove a point, and that is that flux is, as long as the amount of flux generated by these magnets is completely absorbed and by this flux path from north to south is the same as the flux path that goes from the magnets north to south or south to north. That's not important, but the flux path here and equals the flux path here. And that's the secret or the principle of this. As long as the flux is just as happy going in this manner as it is going in this manner, then it will toggle with a very, very little bit of energy that the flux will flip and go the opposite path. So these coils, and again, all the magnets, the metal, the size of it, and the coils is all just arbitrary, picked out of the air for now, just to prove the point. If the principle works as I see that it would, then the dimensions of everything, the coils, the metal, and everything, all these parameters have to be looked at and determined what is the most efficient way to do it. But if it just works is the main thing, then it can be taken care of from that. So, these, there are more magnets, by the way, to be added. They're out here, if you can get them. And that's why this is adjustable, where we can add more magnets or less magnets for various testing. I also have, over there, you see the stack of metal in the corner over there? Okay, those 4 pieces over there with the screws in them take the place of these 4 pieces of metal. They're a different type of metal, so it has to be tested with these metal and with that metal. And I think you will find that that metal is actually more efficient at doing the job than this metal will.
What's the difference?
The difference is the softness of it. It's called soft metal, which means that when the flux is moving through or set up in one side of it, and you remove the flux or you transfer the flux away, the metal wants to completely go back to the state that it was instead of staying a magnet. If you took a magnet and magnetized a paper clip, for example, that paper clip is now magnetic and it'll pick up another paper clip, right? Well, you don't want that with this principle. You want to have soft steel, and the term soft means that it won't retain that magnetic principle. And it's very difficult to find metal that will do that. Hopefully this is part of one of them. And that is the best I could find. I think it's called 1008 principle of the number, which is the softest that I could find. And I couldn't find it in a solid piece like this. So I had to get 1/8-inch pieces and stacked up 8 pieces and have them screwed together and then smoothed off and ground to get the same smoothness so they will go together with no air gap in it. And I feel that metal will work better than this metal for proving it, so you have to test both. So basically you take these coils and again they're arbitrary values, and I have 3 different sets of coils to try out just to see which works best. And between this one, which is 24 AWG, American wire gauge, and 28 is equal to twice the size, a little over twice the size. So you should get a difference in flux. The idea is to put a little pulse on these. You put these together in such a way that the north and the south, or the positive and negative, or the beginning and end, whatever you want to call it, are opposite. Let's mark each of these wires plus and minus. Well, you put the minus to the plus and the plus to the minus on these two, and put them aside. Take the same plus and minuses of these two and put them aside. You're going to hook these up so that the reason they're reversed is you're going to look at the output that the flux, when it passes through these paths, the output pulse that you're going to get when that flux passes through, you're going to get a pulse. So when you put these together opposite like that, the pulse will always be in this right same direction. So negative will come out positive, positive will come out negative. So that way you want to get the output pulse from these coils and the input pulse from these coils. Hopefully, the adjustment that you start out with, you use a flux meter here. This flux meter, by the way, costs $500. Very expensive. And purpose of the flux meter is to actually see how much flux is going through a path. So when you're setting this up to run the test, you need to see.
Try to separate them?
Yeah, here we go. You measure the flux with this guy here, and you can see the reading the flux, 1950. So that's telling you how much these magnets are actually moving from here through the end of this and trying to find a way back to the other side of the magnet. So that's just an arbitrary number for now. But what you have to do is to set this so you have exactly, to the most accurate as you can get it, the same amount of flux has to be set moving arbitrarily when it's sitting still like this. So that's the most critical measurement, is to balance the flux. That's the whole secret of it. So the flux will be so happy to go this way, or it will be just as happy to go that way. You notice when I try to get it apart, one was more than the other. So as I put this back on here to get it, then this one is very, very hard to take apart. But once I get it apart, then it goes back together and it's not as difficult to take apart. So the whole principle is balance the flux so it doesn't matter which path it goes. And to do that, once you've got it balanced, a tiniest little pulse, in my mind, is the whole thing. The tiniest little pulse in these coils, and the reason I say two coils is when you put this pulse in, you're going to be telling, if the flux is over here right now, let's pretend the flux is going this way, you're saying to this path here, I don't want you coming this way, and you actually, the pulse will be rejecting the flux and creating opposite flux so that it tries to force it into the opposite path here. And simultaneously, since you've got these coils hooked together, when you're telling this one, I don't want you over here, you're telling this one, I want you over here. That's why you have the coils reversed across here. You're pushing one and pulling on the other one over here with the same tiny little pulse. And the reason it only should take a tiny little pulse to do it is because this flux doesn't care which path it goes on. It is just as happy one or the other. So when the flux moves from either one of these two loops back and forth, then it will create a pulse through these coils as the flux changes in the path. And these pulses, depending on the wire gauges and so forth, you should get a very big pulse out of here and take that big pulse and charge a battery with it or a capacitor or whatever. But you use the charge that is generated by this flux collapsing. So hopefully you charge these pulses, charge a battery, take this battery and take a little bit of that battery electricity to generate a pulsar that comes in here and tickles these. Tickle, tickle, tickle. And you can do that just as rapidly as it'll collapse, as the flux collapses. So you can put those pulses in as fast as the coils collapse and go back again. And so as you're doing this with a pulse generator, you're creating pulse, 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 pulse coming out of here and charging this battery. Make sense?
So far.
Understand that? Seem like to you understandable? Okay, well, that's the whole principle of it. Is very simple when you think about it. And the whole thing that I discovered was that the flux, when you first talk to somebody about an arrangement like this, forget about the coils for a minute. If you just said to them, if you had a magnet and you have two metal paths like this, they would instinctively tell you that probably half the flux goes one way and half goes the other and splits up. But it's not true. All the flux is happy in one side.